All about chiral spintronics.
Sounds complicated.
It can be, but it's really cool. Think faster, smaller, and way more efficient electronics, all thanks to, get this, the handedness of molecules.
Handedness, like left or right.
Exactly. We've got some really interesting research and overview articles on this, so let's break it down.
Sounds good.
So you mentioned handedness.
Yeah.
That's something called chirality, right?
You got it. Scientists are getting super excited about this unique property of molecules. Like, think about your hands. They're mirror images of each other, right?
Yeah.
But you can't perfectly stack them on top of each other no matter how you twist them.
That's true.
That's chirality in a nutshell. And guess what? Molecules can be chiral too.
Wow. Okay, so we've got these chiral molecules, but how does that help us build better electronics?
Well, the magic happens because of something called the chiral-induced spin-selectivity effect.
Try saying that 5 times fast.
Haha, right. CISS for short.
Much better.
Basically, these chiral molecules act like a filter for the spin of electrons. Like a gatekeeper.
Okay, so electrons spinning one way get through and the others get blocked.
Exactly.
So could you maybe explain how that actually works? How does the structure of the molecule create this filtering effect?
Sure. Imagine an electron trying to travel through a chiral molecule, right?
Okay.
The way those atoms are arranged inside the molecule creates a specific path for the electron, kind of like a maze.
And because the molecule is chiral?
Right. So as the electron travels, it interacts with the electric field created by the atoms in the molecule.
Okay, I'm following.
But here's the thing. This interaction changes depending on which way the electron is spinning.
So the electron's spin determines if it can get through the chiral molecule maze.
Exactly. That's a great way to picture it. And this is where things get super exciting, because by using chiral molecules, we can potentially control the flow of spin without needing traditional methods like magnets.
That's incredible. So we're essentially controlling things at the molecular level. One of the papers we looked at mentioned terbium oxide as a material with a lot of potentials. They call it a high-temperature multiferroic material, which sounds pretty intense.
It does, doesn't it?
Could you break that down for us?
Multiferroic basically means that the material has both ferromagnetic and ferroelectric properties.
In English, please?
Haha, sure. It means the material can have a permanent magnetic field, and it can also be electrically polarized.
Okay.
Now, most materials that have these properties only work at extremely low temperatures. Not exactly practical for everyday use,
Right.
but terbium oxide, this one's special. It keeps those properties even at much higher temperatures.
So it's kind of like a 2-for-1 material, magnetic and electric, plus it can handle the heat.
Exactly. And that's what makes it so exciting for chiral spintronics. It opens up so many possibilities for devices.
Devices that are not only smaller and more efficient, but also can handle different temperatures?
You got it.
Okay, so we're starting to see how the science of chirality and these materials like terbium oxide all fit together. But let's talk applications. One of the most fascinating ones mentioned was spintronic memory.
Yeah, that's a big one.
Right now, our memory devices store data as electrical charges.
Right.
But with spintronic memory, we could use the spin of electrons instead.
And that could mean a huge jump in how much data we can store. Plus, it uses way less energy.
So instead of just a 1 or a 0 based on a charge, we could have more possibilities based on spin.
You got it. Imagine a smartphone that could hold everything you could ever want to store.
And without needing a charge every 5 minutes, that's a game changer.
Absolutely.
But memory is just one piece of the puzzle. What are some other areas where chiral spintronics could revolutionize technology?
Well, what about transistors? Those are the essential building blocks of pretty much all our electronics today.
Right.
They control the flow of electrical current, but imagine controlling the flow of spin instead.
And that's where chiral spintronics comes in.
Exactly. These new spintronic transistors would not only be smaller and faster, but also unbelievably energy efficient.
So computers and smartphones could be hundreds of times faster and more efficient than what we have now.
It's definitely a possibility. And we could also see completely new functionalities, things we can't even imagine right now.
Now we're talking. But speaking of things that sound like science fiction, what about those molecular qubits we read about? That could revolutionize quantum computing, right?
You're right, it could. Quantum computing uses the principles of quantum mechanics to solve problems that are impossible for even the most powerful computers we have today.
And these molecular qubits could be the key.
Exactly. And they're made possible through chiral spintronics.
So we could be talking about solving problems that are way beyond our reach right now. Everything from developing new medicines to creating entirely new materials.
The possibilities are pretty mind-blowing. And the really crazy thing is that we're just scratching the surface with chiral spintronics.
That's kind of terrifying and exciting all at the same time.
It really is.
It sounds like we're on the verge of some serious breakthroughs, but I imagine there are some challenges too, right? It can't be all smooth sailing.
Oh, absolutely. One of the biggest hurdles is actually finding the right materials to work with.
I could imagine that.
we need materials that show this strong chiral-induced spin selectivity we've been talking about.
Right, they need to be good at filtering those spins.
Exactly. But they also need to be stable at room temperature.
Makes sense. We can't have electronics that only work in a lab freaker.
Exactly. And we need to be able to use them with our current manufacturing processes.
So it's not just about finding something that works, but something that can be scaled up for mass production.
You got it. And a lot of research right now is focused on bridging that gap between lab discoveries and real-world applications.
I can see why that's a huge focus. Now, one of the things that really caught my eye in the research was this technique for actually visualizing spin waves.
Oh yeah, that's pretty wild.
They're using an electron microscope coupled with microwave technology.
It's like we can see the dance of the electrons at the nanoscale.
Seriously.
Imagine you've got a surface covered in electrons, all with their spins pointing in the same direction.
Okay, I'm picturing it.
Now you introduce a little disturbance, like a pulse of microwaves.
And that creates a wave.
A spin wave. It's like when you drop a pebble into a still pond, and you see those ripples spreading out.
That makes sense. So we're essentially creating these spin waves and then watching them with the electron microscope.
Exactly. It gives us a direct view into how spin works in different materials and how we can control it.
It sounds like a powerful tool for research, and that brings us to magnonics, which uses these spin waves for information processing.
Right, magnonics. That's where things get really interesting.
It sounds like a whole new way of thinking about computing.
It really is. Instead of moving electrical charges around, like in our current electronics, we use these spin waves to transmit and process information.
So instead of electrons flowing through wires, we have these spin waves carrying the data.
Exactly. And because spin waves can travel so much faster and with less energy loss than electrical currents, magnetic devices could be incredibly powerful.
That's amazing. So we've talked about memory, transistors, even quantum computing. Are there other areas where chiral spintronics is making waves?
Oh, tons. Sensing technology is a big one. Imagine sensors that can pick up tiny changes in magnetic fields or even detect specific molecules.
All thanks to the chirality of the materials.
You got it. Think about the possibilities for medical diagnostics, environmental monitoring, security systems.
The applications seem endless.
They really do. And then there's energy harvesting.
What, like solar panels?
Similar idea, but using chiral materials to convert things like waste heat or light into electricity.
So not only could chiral spintronics make our devices more efficient, but it could also change how we generate energy.
Exactly. It's pretty remarkable stuff, but we do need to remember that this field is still quite young.
Right, we're still in the early stages.
There's been a lot of progress, but there's still a long way to go before we see chiral spintronics in our everyday devices.
I understand. But the research is moving fast, right?
It really is. And the future looks incredibly bright for chiral spintronics.
It's almost like standing on the edge of a new frontier with all these possibilities stretching out before us.
Exactly. It makes you wonder what the world will look like in 10 years or 20 years when this technology really takes off.
It's mind-blowing, really. But before we get too carried away with the future, I think it's important to consider some of the bigger implications of all this. We've been talking about all the positive stuff, but
Yeah.
I mean, any new technology,
Right.
there are always potential downsides too, right?
Absolutely. With great power comes great responsibility, as they say. And with chiral spintronics, there are some big ethical considerations we need to think about.
Like what?
Well, data security and privacy, for one.
Yeah. If we're talking about devices that can store way more information,
Exactly.
we need to make sure that information is protected.
Absolutely. And we need to make sure this technology benefits everyone. We don't want to create a new digital divide.
Right. Accessibility is crucial. It's something we need to keep in mind as this field develops.
For sure.
Okay, so we've covered a lot of ground today, from chirality to quantum computing. It's been quite a journey.
Yeah, it has.
For our listeners who want to learn more, where would you recommend they start?
Well, there are a lot of great resources out there. I'd say start by checking out the work of some of the leading researchers in this field.
Okay.
There are some excellent review articles that give you a good overview. And don't be afraid to dive into the actual research papers. They can be a bit technical, but it's worth it to stay on top of the latest discoveries.
It's good advice to go straight to the source. Now, as we wrap up our deep dive into chiral spintronics, what's one key takeaway you'd want our listeners to remember?
I think the most important thing to remember is this. We're still at the very beginning.
Yeah, this field is still so young.
Everything we've talked about today, it's really just the tip of the iceberg. There's so much more to discover and explore.
It's pretty exciting to think about all the possibilities that lie ahead.
It really is. We've learned that we can control the spin of electrons using chirality. Who knows what other secrets of the quantum world we'll unlock next?
It's almost overwhelming to think about.
And that's what makes it so exciting.
Well, thank you so much for joining us on this deep dive into the world of chiral spintronics. We hope you've enjoyed it as much as we have.
It's been a pleasure. And remember, the quest for knowledge never ends. Keep exploring, keep asking questions, and you never know. Maybe you'll be the one to make the next big discovery in chiral spintronics.
That's a great note to end on. And that's all for this deep dive, folks. We'll see you next time for another exciting adventure into the world of science and technology.